The brain's favorite energy source is glucose. Although the brain can use ketone bodies, it cannot use fatty acids because of the blood-brain barrier. In addition, the brain will access ketone bodies only when they reach quite high concentrations in the bloodstream. In fact, when glucose in the plasma drops, the brain sends instructions through the hypothalamus and the autonomic nervous system to the pancreas and adrenal glands, releasing glucagon, epinephrine, and cortisol, and instructing the liver to restore plasma glucose by glycogenolysis and gluconeogenesis. Plasma glucose is maintained somewhere between 80 and 100 milligrams per deciliter. This happens because of the effects of glucagon and epinephrine on the liver's glucose output. Under the influence of these two hormones, the liver's two pathways responsible for restoring blood glucose, namely glycogenolysis and gluconeogenesis, are both activated. By restoring blood glucose, the liver provides key tissues like the brain and red blood cells with the glucose they need as their major energy source. During sleep, we are essentially fasting for about 7 to 8 hours. For the brain to meet its energy needs and maintain its normal functions during sleep, it absolutely needs glucose as a source of energy. In the absence of dietary intake of carbohydrates, the liver's main function is to provide glucose to the bloodstream so that tissues like the brain can use it. The liver will be increasing ketone body synthesis, ketogenesis, because it's using fatty acids as a source of energy, producing a lot of acetyl-CoA, and some of that acetyl-CoA is used in ketogenesis. So note how important the liver is. It's providing glucose, providing ketone bodies, two different forms of energy to other tissues to use during fasting. The liver detoxifies alcohol by converting it to acetaldehyde and acetic acid. The excess NADH produced during the process will be used to divert 3 gluconeogenic precursors away from gluconeogenesis. Pyruvate, oxaloacetate, and DHAP are all intermediates in gluconeogenesis. So you are depriving the precursors of gluconeogenesis, removing the precursors of gluconeogenesis due to the excess NADH. If you don't have gluconeogenesis, you cannot resupply the blood with glucose, resulting in hypoglycemia and impairing brain function. If you like this video, please subscribe. Thank you.